I recently carried out some work looking at the issues of circulating currents that may occur when multiple cable circuits in close proximity are operated in parallel to supply a common load. I have prepared this short tutorial video to raise awareness of this issue. There are 3 parts to this tutorial. I shall look at the physics behind the issue, then present the mathematical formation of a matrix equation to determine the cable currents. And finally, I will use my implementation of the matrix equation to demonstrate the circumstances where circulating currents may be problematic. When there are multiple paths between a source and a load, the currents will divide between the paths such that the current in each path is inversely proportional to the impedance of the path. Simple circuit analysis tells us this. When cables are arranged in parallel supplying a load, there will be a mutual reactance between the phases, and this mutual reactance increases as the distance between the conductors gets smaller. The AC voltage drop in one cable conductor due to the AC current in a second cable conductor increases with the current in the second circuit. And this is basically a voltage induced by transformer action, i.e. it's an example of Faraday's law. The alternating current in the first conductor sets up an alternating magnetic field, and this alternating magnetic field induces a voltage in the second conductor. Now this leads to the concept of mutual reactance, which relates the AC voltage induced in one conductor due to the AC current in another conductor. If we consider operation at a single frequency, we can use phasor equations to define the mutual reactance. This leads to the expression E2, the induced voltage, is J times the mutual reactance X times the phasor expression for the inducing current I1. The J term gives the correct phase angle relationship between the inducing current and the induced voltage. The total voltage drop in a single conductor is the sum of the voltage drop due to its self-impedance and the voltage drops due to the mutual reactance with every other current-carrying conductor. If the conductors are not arranged so that the mutual reactances are equals, the conductors form a non-symmetrical configuration. In a non-symmetrical configuration, the load current will not divide equally between the parallel circuits, and this results in current unbalance among the phase conductors. If we had 2 3-phase circuits and we look up the standard textbooks, they will tell us that arranging the conductors A1, B1, C1 of circuit 1 and C2, B2 and A2 of circuit 2 will produce a symmetrical arrangement. And with such a symmetrical arrangement, when we calculate the currents in circuit 1 and determine their sequence components, and we calculate the currents in circuit 2 and determine their sequence components, we will find that with this symmetrical arrangement there is no apparent zero sequence current circulating around the 2 parallel 3-phase circuits. An example of a non-symmetrical arrangement would be to simply lay the conductors in phase order. So in this example we have A1, B1, C1 of circuit 1, followed by A2, B2 and C2 of circuit 2. Now with this arrangement there will be a strong circulating current between the two parallel three-phase circuits. Another way of arranging single core cables is to adopt the trefoil arrangement, where the cable centres are placed at the corners of an equilateral triangle. So if we have a single trefoil, then it is clear that the mutual reactances between the phases will be balanced. If we have two trefoils, which are themselves individually balanced, will the overall circuit comprising of the two parallel three-phase circuits be balanced or unbalanced? Will current circulate between the two individual trefoils which are themselves balanced? And this was the question which originally motivated me to look at this issue. If we consider the electrical characteristics where we have two parallel cable circuits supplying a load, then the electrical connectivity would look like the diagram shown in this slide. So here we have the two parallel cable circuits, phase A, then we have the B phases, and then we have the C phases. The cables are connected in parallel, as we would expect, and they supply a load impedance in each phase. The start point of the load impedance may be directly connected to earth, or there may be a neutral earthing impedance in the start point. The currents into the circuit are driven by the three-phase EMFs, and these are star connected, and again we may have a neutral impedance at the start point of the source EMF. Now this circuit shows us the electrical interconnections, but it does not explicitly give us any information about the physical arrangement or proximity of the cable conductors. Now, in order to understand what is happening in the circuits where we have two cables operated in parallel, it is necessary to calculate the voltage drops in each circuit. Now, there are a number of paths between the start point at the source and the start point at the load, and I have highlighted in this slide one of the paths in the circuit, and you can see that there are actually 6 of these paths because we have two parallel three-phase circuits. So the first task that we have to do is to calculate the voltage drops in the circuit which I've highlighted in blue. So obviously there will be current flowing down the A1 conductor. that current will cause a voltage drop in that conductor due to the self-impedance of the conductor. So that gives us this voltage drop term here. There will also be a voltage drop in the cable conductor due to the currents flowing in every other conductor in the two three-phase cable system. So we will have current flowing through the conductor labelled A2, and that current will induce a voltage drop in the conductor A1. So the current in A2 times the mutual reactance between A2 and A1 will give us the voltage drop in A1. And that is this term here. Of course, there will be currents flowing in every other conductor. There will be different mutual reactances between A1 and these other conductors. And these mutual reactance and the other currents will all cause a voltage drop in A1. So we have all these terms here. Now there will be a voltage drop across the load impedance. In phase A, the current which is flowing through the load impedance in phase A will be the sum of IA1 and IA2. That gives us this voltage drop here. Now the sum of IA1 and IA2 will flow towards the star point. The same will happen with IB1 and IB2, and the same will happen with IC1 and IC2. So the current which flows into the neutral impedance will be the sum of I1, I2, IB1, IB2, IC1 and IC2. So we have to sum all those currents together and multiply them by the neutral impedance to get the voltage drop across the neutral impedance. And that is this term here. And finally, we get the same summation of currents at the neutral at the sending end, and we add those currents together to get the voltage drop across the neutral impedance at the sending end, which gives us this equation here. Now it's clear from this slide that even looking at one conductor of the 6 conductors in our two three-phase circuits, that the voltage drop becomes quite complex. In actual fact, because we have two parallel three-phase circuits, we arrive at a system where we have to consider 6 self-impedances, that is the self-impedance of each conductor, and there are a total of 15 mutual reactances that need to be considered. So once we go through this process for each circuit in turn, we can formulate a matrix equation. And this matrix equation tells us that the source EMFs is equal to the impedance matrix, which is made up of the mutual reactances, the self-impedances, the load impedance, and the star point neutral impedances, multiplied by a current vector, which is the currents in each phase of the 6 cable cores. So if we can formulate this matrix equation, then for a known set of source EMFs, then the currents in each of the 6 conductors can be calculated. And once the currents in each of the 2 3-phase circuits are known, their symmetrical components can be determined using Fortescue's transformation. And this matrix equation method can be extended to consider any number of parallel 3-phase circuits. So the question now arises, how do we calculate the self-impedance and mutual impedance of the cables? Now, there are a number of methods which are presented in the technical literature. Boole's equations, which were published in 1949, are fairly straightforward to use, although they are in imperial units. Now, these apply to stranded conductors. It assumes there is no shielding around the conductors, and it also assumes that there is no earth return path. And when calculating the self-impedance, then we would use the AC resistance provided in the manufacturer's catalogue, and we would calculate the reactive component of the self-impedance from this equation here. The K dash term effectively takes account of the internal inductance of the conductor, that is the associated with the magnetic field, which is internal to the conductor, and this logarithm term is associated with the magnetic field external to the conductor. And you can see that the mutual reactance is calculated in a similar way, and here the key issue is the distance between the conductors. The larger the distance between the conductors, the smaller the mutual reactance. An alternative formulation would be to consider the conductors as being solid conductors, and then if we neglect skin effect, then the following equations can be derived. Here we have the expression for the self-reactance. Mu naught over 8 pi is essentially the inductance of the conductor due to the magnetic flux, which is internal to the conductor, and mu naught over 2 pi times this term here is associated with the inductance due to the magnetic flux, which is external to the conductor. So the term in brackets gives us the total inductance. We multiply that by omega to give us the reactance, and then we multiply that by the length of the circuit to give us the overall reactance. To form the self-impedance, we would add this self-reactance to the resistance of the cable, and again we would use the AC resistance from the manufacturer's data. Again, like Bohr's equations, we are assuming there is no earth return path. We get this equation for the mutual reactance, which again shows us that the mutual reactance decreases as the distance between the conductors increases. If we want to take the analysis a little bit further, then we could model a single conductor and we could include the skin effect. Now, in this case, we don't use the AC resistance of the cable. Instead, we use the DC resistance. And from the DC resistance of the cable and its radius, we can determine the conductivity of the cable material. We then substitute the conductivity of the material along with the permeability of the material and the frequency at which we wish to do our calculations into this equation here, and this gives us M, which is a complex number, and it is the reciprocal of the depth of current penetration into the conductor. We then take this complex number M and substitute it into this equation, which uses the hyperbolic cotangent function, and this equation will give us the real and imaginary parts of the internal impedance. So to form the total self-impedance of the cable conductor, we take the real and imaginary parts of this expression. So this gives us the resistance, this gives us the reactance due to the flux which is internal to the conductor, and this expression gives us the reactance due to the flux which is external to the conductor. And for the mutual impedance, we are using the same equation as before. So we have three different ways of calculating the self and mutual reactances of the cable conductors. So let's look now at some calculations. So this is a small program which I have written, which allows us to examine the characteristics of parallel cables. This program is written in Silverfrost Fortran 95, and it uses the Silverfrost Clearwin Plus graphics library. And the program can be used to examine the current division between up to 4 parallel 3-phase single core cable circuits. So here we see the system parameters. We specify the frequency, the nominal voltage, the load current which is to be supplied and its power factor, the length of the parallel cable circuits, information about the treatment of the source start point and the load start point, and finally the set of equations which are to be used for the calculation of the self and mutual impedances. Each individual cable circuit is defined by the coordinates of the cable and the diameter of the conductor core, the AC resistance of the cable at rated frequency, the DC resistance of the cable, and also the external diameter of the cable. We don't use the external diameter of the cable in the calculation, but we do show it in the graphics, and that's a check to make sure that the coordinates which are entered here are realistic and we don't have the cables overlapping each other. So in this example at the moment there are just two cables in service, and we have specified that we are supplying a total load current of 400 amps. Sorry, 4000 amps. So let's see what happens when we run the calculation for this cable configuration. And note that here we have the cable conductors in a flat formation in phase order. So A, B, C for circuit 1 and A, B, C for circuit 2. So let's run the calculation. And at the moment with this configuration, both the start point of the source and the load are solidly earthed, which means there will be a flow of earth return currents, and the equations which we've presented to do this calculation may not be valid. However, we'll ignore that warning for the time being and let's look at the results. So circuits 3 and 4 are out of service, so their currents are all 0. We can see the currents in circuit 1, phase A, B and C, and the currents in circuit 2, phase A, B and C, and clearly these are not balanced. If we calculate the symmetrical components of these currents, we can see the positive sequence current in circuit 1 is less than the positive sequence current in circuit 2. We also have a very large zero sequence current flowing between the two parallel circuits. 269 amps in circuit 1 and 265 amps in circuit 2, and these are nearly 180 degrees out of phase. So it would appear as though there were zero sequence circulating currents between the two cables. And there is also some negative sequence current. If we sum together the currents in each phase of each circuit, that gives us the total load current. Again, the load currents are slightly unbalanced. The total positive sequence current in the load is 4000 amps as we've specified, and the voltage which is required to circulate that current in the load is actually 1.6 times above the nominal system voltage. Now, of course, we don't know the voltage drop across the cable before we do the calculation, so there is a little iterative calculation undertaken to find the required sending voltage to circulate the specified load current. Now, we've spoken about taking the symmetrical components of the currents in each circuit. Now, the symmetrical component transformation is simply a change of reference frame, and the presence of negative sequence and zero sequence currents can be used to identify the presence of unbalance on a power system which might occur, for example, during fault conditions. Now, in this case, there is no fault on the system, and the zero sequence currents calculated in the cable circuits, approximately 269 amps, calculated using Boole's equations, is due to the unbalance in the cable mutual impedances. We could do the calculation assuming a solid conductor with no skin effect, and when we run the calculation we now get 269 amps. So there is really no difference between using Boole's equations and modelling the conductor as a solid conductor. And if we model the conductor as a solid conductor with skin effect, then again we will see that the circulating currents, or the current unbalance, is almost the same as the value which would be calculated using Boole's equations. So we come to the conclusion that Boole's equations are good enough for the analysis. So we will use these for the remainder of the examples which I will demonstrate. Now, if we just run this simple case once more, we're getting the warning that both the star point of the source and the neutral are earthed, and we can see that we have a zero sequence component of current flowing at the load. Now we can eliminate this by specifying that the load star point is isolated, and this is quite reasonable. Normally we would expect a delta connection on the transformers which are supplying our downstream load, and of course those transformers would block the zero sequence component of current. So having made that change, if we run the program again, we've now eliminated the zero sequence component of current in the load, and we can see that we still have the zero sequence component of current in the two three-phase circuits, and the zero sequence currents are identical and 180 degrees out of phase. Now remember that the presence of zero sequence currents will be used by the protection system to detect the presence of an earth fault. And with this flat configuration of cables, it would appear to the protection system that there was an earth fault on both cables, and this could lead to the tripping of both cables and loss of supply to the load. Now in this example, the nominal voltage is 4.16 kV line to line. In order to limit the potential earth fault current to a value of say less than 25 amps, a resistance of 100 ohms could be placed in the neutral of the source. So if we implement this in the model, so we specify an impedance for the start point and we make it 100 ohms. So now if there was an earth fault on the cable, the zero sequence current during that earth fault would be limited to 25 amps. But if we now run the analysis, we see that the zero sequence circulating current between the cables is unchanged, and the zero sequence circulating current exceeds the maximum value of the zero sequence fault current which we would expect on the system. So this makes the presence of these zero sequence currents due to circulating zero sequence currents more challenging to deal with from the perspective of the protection system. Now, a key issue is the proximity of the circuits. If we were to move the position of circuit 1 by half a meter to the right in this diagram, so let's displace all the cables in circuit 2 to the left, or to the right even. What happens now when we run the program? So we can see that with the increased separation between the two flat groups of conductors, the zero sequence current is decreased from what was previously 267 amps to 75 amps. And this is due to the effect of the logarithm of 1 over the distance between the conductors in the equation for the mutual reactance. Now, I'm just going to put these conductors back to their original positions. And make sure that's right. So we're getting back to 260 amps, 67 amps, zero sequence current. Now, at the moment, we have an unsymmetrical arrangement. So we have A, B, C of circuit 1 followed by A, B, C of circuit 2. Let's make this a symmetrical arrangement by swapping the positions of conductors A and C in circuit 2. So if we swap A and C, we now have a more symmetrical arrangement. We have A1, B1, C1, C2, B2, C2. Let's see what happens when we run the calculation. So now, with the position of these two conductors swapped over, the zero sequence current is now 0. Note, however, that there is still a small residual negative sequence current, and this is due to the flat arrangement of the conductors. If we were to run with just a single cable in circuit, so let's take cable 2 out of circuit, we're just left with cable 1, run the analysis again, so we have a warning there is only one cable in circuit. You can see that there is no zero sequence current now. Cable 1 is supplying the full load current of 4000 amps, and we have 27 amps of negative sequence current. And as I've said, this is due to the flat formation of the cables. Now I can demonstrate this because I could convert this flat arrangement to a trefoil arrangement with the same spacing between the conductors. So let's do that. So if I take the distance between the conductors and define a trefoil with that spacing, so there's my trefoil, and if I now run the analysis, again there's only a single circuit in service, but you can see that with that symmetrical trefoil, the negative sequence component of current is now eliminated, and in this case we have a perfectly balanced three-phase system, and our system has perfectly balanced impedances. So what happens if we introduce a second trefoil? So let's put circuit 2 back into service, and we will make it a trefoil with the same spacing as circuit 1, and let's center that trefoil at 0.4 meters from the center of the first trefoil. So let's see what happens now. So we've run the analysis, and we can see that once again our zero sequence current has reappeared, and now we have 122 amps circulating around two parallel circuits. Now let's go back to the diagram. Here we have circuit 1, A, B and C, and here we have circuit 2, A, B and C. So the phase order of the conductors is the same. Remember, with the flat formation, when we made the circuit symmetrical about the centre line between the two groups of cables, then the zero sequence current was eliminated. And at the moment, this configuration is not symmetrical about the centre line. But if we swap the positions of A2 and C2, then the system will be symmetrical about the centre line. So if I swap A and C, so I have A1, B1, C1, A2, B2, C2, it is now symmetrical. If I run the analysis, the zero sequence currents are eliminated. So these examples demonstrate that the zero sequence current, which will circulate between the three-phase circuits, is very, very sensitive to the phasing of the individual conductors in the three-phase circuits. So, summarising the examples that we've looked at, if we have a flat formation ABC, ABC, we have a strong zero sequence current. And this configuration has the largest unbalance of all those that we have considered. If we swap the positions of A and C to create this flat arrangement, which is symmetrical about the centre line, the zero sequence current is eliminated. If we have two trefoils with identical phase order in each trefoil, then we will get a large zero sequence component of current. If we have two trefoils and we arrange for the phasing of the conductors to be symmetrical about the centre line, then we do not get any zero sequence circulating current between the trefoils, and we get the minimum negative sequence current. So comparing these four arrangements, the maximum asymmetry occurs with this arrangement here, the flat arrangement ABC, ABC, and the minimum unbalance occurs with this trefoil arrangement here, with the circuits arranged symmetrically about the centre line. So to summarise this discussion, when there are multiple conductors per phase, then the currents will not necessarily divide equally between the phases. It will divide depending on the effects of mutual reactances between all the conductors. And this can result in current imbalance among the phase conductors. As a consequence of current imbalance, zero sequence currents can flow around the parallel circuits. And this can be seen by the protection systems for the cables, and it may be interpreted as a cable earth fault. Even in systems where the maximum cable earth fault is limited by a neutral earthing impedance, we can still get circulating currents which appear as zero sequence currents, which far exceed the zero sequence current that would be expected during a cable earth fault. Now, these circulating currents can be readily calculated using the matrix method that I've presented, and we can use the program to find the best arrangement of up to 4 cable circuits, 4 three-phase cable circuits, so as to minimize any current imbalance and circulating currents. However, the difficulty with this is, of course, that whilst you might be able to minimize the circulating currents, let's say with all 4 circuits in service, when one circuit is taken out of service, then unbalanced conditions will arise. So if the currents in the cables cannot be balanced, then it may be necessary to introduce transpositions to the cable circuits. The other thing to note that the presence of circulating currents changes the current distribution between the phase conductors. Some will run hotter than others. So a knowledge of circulating currents is necessary when considering the thermal aspects of any cable installation. So I hope you found this tutorial interesting. If you want to explore this topic further, then I've listed a number of useful references on this slide. Possibly the easiest paper to start with is the one by Petty, which I've highlighted here. So I hope you found that interesting, and I might do another video such as this in a few months' time. Thank you.